Using flow simulation, we'll set up a heat transfer study to look at the effectiveness of this heat sink. But before we dive in, we need to address the fine geometric details, specifically the fins, which are just 0.05 inches thick, and the 0.7-inch gaps between them. Now, this gives us an excellent opportunity to take advantage of the AutoMesher's advanced capabilities, which allow us to efficiently capture these small but critical features without manual mesh refinement. Let's start with the wizard. Trust me when I say no matter how advanced you are or complicated the study, start with the wizard. It's only your starting point, but it sure is the easiest way to set up all the prerequisite stuff. This third page is where we check the boxes to include the necessary things in our study. This is a heat transfer study with a solid, so we'll check conduction, and also we can't forget gravity. Warm air rises, right? Well, this is caused by the buoyancy effects of air. Just turn on gravity in the correct direction, and flow simulation will automatically take care of this. Lastly, this is an external study with air flowing around the solid, not through it like an internal study. Just make sure it's set accordingly. Moving on to the materials. First is the fluid, air, and then the solid, aluminum. Last is the initial and ambient conditions, which set the starting point for the study. Now, we're only partly set up. We still have some work to do. Start at the top and work your way down the flow simulation tree. The computational domain is the area solved by the software. A lot of interesting stuff will happen above the heatsink, so let's extend the domain to make sure we capture all that. Next, we need to add some heat to the heatsink. That would be a heat source, but you'll notice it's not shown here in the tree. That's because this is the default out-of-the-box setup for flow. You can add or hide things here by clicking Customize Tree. Let's add a 100-watt volume heat source to our solid. Now, we're ready to finish the setup by adding a goal to measure the temperature. Now, this step isn't required by flow, but it's highly recommended to the point where it should be. It ensures the results you're most interested in are the most accurate through solver convergence, and it makes it easier to quickly get these results through goal plots. At this point, the simulation is ready to run, but let's take a moment to dig into the auto mesh. Right-click on Global Mesh so we can refine the settings. First, to account for gaps between the fins, remember we measured it to be 0.7 inches, let's key that in here. And if you want to refine this even more, you can increase this slider from the default 3 to 4. Let's create the mesh and see how this does. Looking at a cut plot, we can see how well it did with the geometry. And it's okay, but we can do better. Let's go back in there and continue with the auto mesher. And this time, we'll use the advanced channel refinement box and even increase the mesh slider to 5. This will take care of it nicely. And now we're ready to run our study and look at the results. First, let's visualize how the fluid flows using a cut plot, showing both velocity and density. The air is being heated by the heatsink, and as a result, the warmer air will rise. And this is all taken into account automatically because we included gravity. One thing that's super complicated with these heat transfer studies is the heat transfer coefficient. Now, this isn't a required input. We never keyed it in. With flow simulation, it's solved for automatically when there's heat transfer between solid and fluid, like the aluminum heatsink and the surrounding air here in this study. Now, let's get the max temperature. That was the goal of the study, remember? Max temperature in the heatsink. And lastly, a great visualization of the fluid flow with flow trajectories. Picking the top face to trace points through the area, we'll plot temperature. By playing this, we get true insight into how the fluid flows around the heatsink. Flow simulation is incredible at doing the heavy lifting for you and giving you accurate results. In this study, we used the auto mesher and solved for complicated physics like natural convection and the buoyancy effects of air. You don't have to choose between speed or accuracy. With flow simulation, you can have both.